present here. Now our resource person, Professor C.V. Parameshwaran Sankaran, welcome you sir. He did UG at Vivekananda College, Chennai, and he did MSc, IIT Madras, and he did PhD, University Canada. Until he is a professor of Institute of Mathematical Sciences, Chennai, and he was a fellow of Indian Academy of Sciences since 2007 and fellow of National Academy of Science since 2006. And his area of research interest topology, algebraic geometry, and representation theory. And he published over 50 research articles in various national and international journals. Welcome you, sir. Now I request our principal, sir, to honor our chief guest.
Dear professors, I want to talk only a few things which I have shared with the delegates. தமிழே சொல்லுங்க, அதான் நல்லது. ஏன்னா தான் முழுக்க சொல்ல முடியும், சொல்ல வேண்டிய விஷயம். நான் பார்ட்டிசிபேட்ஸ் கூட பேசிட்டு இருக்கிற போது அவங்களுடைய எப்படி இருந்துச்சு, எப்படி பாஸ் இருந்துச்சு அப்படின்னு கேட்டபோது அவர் பெரிய ப்ரொஃபஸர் அவர் சொன்ன விஷயத்தை சொல்லணும். அவங்கெல்லாம் பெரிய மகான், அவங்கெல்லாம் பெரிய மகான். அவங்கள நான் பார்க்கறதே பெருசு. நம்பர் 1. நம்பர் 2, அவங்க சொல்றத கேட்கறதுக்கு எவ்வளவு ஒரு கொடுத்து வச்சிருக்கு பாக்கியம். 2வது விஷயம் சொன்னாங்க. 3வது விஷயம் சொன்னது எனக்கு அதை விட அப்கோர்ஸ் எனக்கு பெரிய இருந்தாலும் உலகத்திலேயே மேத்தமெட்டிக்கல் ப்ராப்ளம் வந்தா அந்த ப்ராப்ளத்தை சால்வ் பண்ணக்கூடிய அல்லது இதுதான் சொல்லக்கூடிய விடை சொல்லக்கூடிய அத்தாரிட்டிஸ் சாதாரண விஷயங்களை இருக்கிறது எனக்கு ரொம்ப ரொம்ப சந்தோஷமா இருக்கு. I must thank to Geeta, student Geeta, Parvati, Anita, உண்மையிலே I'm thankful to them because இந்த மாதிரி ஒரு ஃபங்க்ஷனை நடத்தணுங்கிறது ஒரு வாய்ப்பு கொடுத்து இவ்வளவு பெரிய ஒரு மகான்களை அவங்க சொன்ன அதே வார்த்தையை சொன்னாங்க. நான் மகான்களை வர வச்சது இந்த கல்லூரியினுடைய பாக்கியம், எங்களுடைய பாக்கியம், நம்முடைய பாக்கியம் சொல்லிக் கொண்டு உங்களுக்கு முன்னால் நான் நிற்கிறதுக்கு இவங்களை தேங்க்யூ.
S is a sigma algebra. What does this mean? That S is a subset of the power set, the set of all subsets. So X must belong to S, and if E and F are in S, then E minus F is in S, and EI, I equals 1 to infinity are in S, then union I equals 1 to infinity EI. This is what is known as closed up under countable unions. Of course, because X is in S and differences are in S, so this implies if E is in S, then E complement is also in S. Because X minus E is E complement. Similarly, if I take the intersection I equals 1 to infinity EI, its complement is union I equals 1 to infinity EI complement by the De Morgan laws. And since EI is in S, EI complement is in S, and therefore countable unions are in S, so this belongs to S. So its complement is also in S, that means intersection EI is in S. So if it is closed under countable unions and differences, then it's also closed under complementation and countable intersections. Okay? Converse not true, but this is. So such a thing is called the sigma algebra, and a set S provided with the sigma algebra is called a measurable space. Then I told you that given any class of subsets in the power set of X, there is the smallest sigma algebra generated by it, and that is called sigma algebra generated by it. Now, one very special class of sets are what are called the open sets, namely the topology. Suppose you have a topological space, then you have a very important class of sets called the open sets. So, if K equals open sets in a topological space, then S of K has a special name. This is called the Borel sigma. So it is the smallest sigma algebra which contains all the open sets. Next, we define what is called a measure. So you need a measurable space to define a measure, obviously. So measure is a non-negative thing, and it can take value plus infinity also, and then mu of the empty set is 0. And the most important property is what is called the countable additivity. That means if EI are in S, EI intersection EJ empty for all I not equal to J, then we say that the measure of the union of the EI is the sum of the units. Okay. And I gave you two examples of measures. One is the counting measure, which just says the number of elements in the set. The other is the Dirac measure, where you distinguish one point and the measure of a set is either 0 or it is 1, depending whether x0 is not in that set or x0 is in that set. So these two are two examples. Today we will want to see what is some idea about the Lebesgue measure. Okay. Before I do that, let me just some properties of abstract properties of measures which are important. So let us just look at them.
Sir, one second.
And if E is contained in F, then mu F is bigger than or equal to mu of E. Because F can be written as F minus E union E, and this is disjoint. Therefore, sum of mu of F will be mu of E minus F plus mu of E. So mu of F equals mu of F minus E plus mu of E. So if mu E is finite, then mu of F minus E equals mu F minus mu. So you may be wondering why I am making a fuss, because if mu E is infinity, then both sides are infinity and there is no meaning in subtraction. So only when one of them is finite, subtraction is meaningful. Okay, otherwise you cannot subtract, you can say nothing. So if mu E is finite, then you can subtract. Second property, so this is called monotons. Bigger the set, bigger the measure. That is monoton. Second property is called subadditivity. So we said that if the EIs are not disjoint, the measure of the union is the sum of the measures. What happens if they are not disjoint? Okay. So let us say E equals union EI. Then I define Fi equals no need to define the Fi. Then I define G1 equals E1 and Gi equals Ei minus union I equals 1 to j equals 1 to I minus 1 of Gj. So what I am doing, G1 is E1, Gi is Ei, but I am subtracting all that has already been accounted for in the earlier sets. So this means that all the Gi's are disjoint. Because Gi will have nothing to do with the previous sets. So all the Gi's will be disjoint. But the union of the Gi's is the same as the union of the E's. Because I am not losing any point. I had Ei, I am only removing those which I have already accounted for. Okay, so. But these are disjoint. So mu of union Ei equals mu of union Gi. But this can be the sigma mu of Gi because they are disjoint. But Gi is a subset of Ei by monotonicity, so you get this as a sigma mu. So this is called subadditive. So if you have E is the union of some subsets, then mu of E is less than or equal to the sum of the measures, which is normal. Suppose I have various intervals, they may be overlapping. The length of the union of all these intervals is less than or equal to the sum of the lengths of all these intervals. But if the intervals are disjoint, then it will be equal to the loop. Right? Another very important property. Sets, so sum of the measures is the measure of the union. Therefore, this is equal to limit n tending to infinity mu of union I equals 1 to n Ei minus Ei. But what is that union? It's just En. So this is limit n. Similarly, you have continuity from above. If E1 contains E2, contains E3, and so on, and mu of E1 is finite, then limit n tending to infinity of mu of n equals mu of the intersection of n. How will we prove this? What we will do is take the complement, and for the complement it's an increasing sequence. So we will apply for the union of the complements this theorem, and then take the complement again to get this. But when you are taking complement, you will have to subtract something, and therefore you remember I said one of the sets must be a finite. So some subtraction will come. So I will leave this as exercise for you to do, and you will see why I need mu of E1 is finite, because I will need to subtract something at some stage, and therefore use that property, and therefore. So associated to these two is one useful definition. Suppose En is any sequence of sets. Okay? Now, given any sequence of numbers, you can define lim sup, lim in. Similarly, given any sequence of sets, I can define lim sup and lim in. They are defined in the following. So, lim sup is limit n equals to infinity. You can guess what it should be. Convert the union into intersection, intersection to union. So you get union n equals to infinity. Intersection n equals to infinity. Now using this continuity from above and continuity from below, you can prove the following. Mu of limit n is less than limit mu. And if mu of union pi is finite, then mu of this bigger than the limit. Again, this is necessary because you will have to use the other continuity theorem. So somewhere you will have to need to help. So these are all very simple exercises based on these things. It's good for you to try them so that you get familiar with the hypotheses, the conditions. Okay. So now let us see. I am going to give you a very, very sketchy idea as to how to define the level equation. So what is the idea with which we started why are we doing all this measure theory? We wanted to generalize the notion of the length of an interval. So we must start with intervals. So let me take T, be the set of all intervals of the form A, B, closed at A, open. If you take A equal to B, then it's the empty interval. Okay. So let me take that one. So mu of AB definition is B equals length of the interval. Okay. So now you take R. I can write this as union n plus 1 n is every real number must lie between two consecutive integers. So this is R. So R will be in the smallest sigma ring, the sigma ring generated by C. Okay. So now take any subset E in R. Then E can be covered by countable number of elements. Because R itself is covered by a countable number of elements from B, so any subset of R is covered by. Only it is not unique. Even this is not unique. You can cover it in so many different ways. Okay. Now I am going to define mu star of T equals infimum of sigma mu ei where E is covered by Ei. So every E can be covered by a countable number of elements from E. You can do it in ever so many ways. So I am taking all possible such covers. Each cover I compute the total length of all the intervals which cover it. Take the smallest such one. That I am calling mu star. Is the definition okay? Is the definition clear? This is important definition. So you compute? You take any cover by means of intervals which are half closed, half open. Countable cover. And then you add on the lengths of those intervals. You get some number. Now for every cover you get a number. You take the infimum over all possible. Unfortunately, this is not a measure. Mu star of phi will be 0. Mu star of course of E is greater than equal to 0 or plus infinity. This is true. It also has the monotonicity property. Mu of E is less than equal to mu star of F when E is contained in F. All these are obviously true. But countable activity will fail. What we have only is subadditivity. So if E equals union E, right, then mu star of E is less than equal to sigma I equals 1. So, but we want countable additivity, so we have to do something. So we say, this is the important definition. A subset E in R is said to be measurable if for every A contained in R, we have mu star of A intersection E plus mu star of A intersection. Definition of measurable. So if you take S bar equals set upon collection measurable subsets, it turns out that S bar is a sigma G. That's the important theorem of Karathy-Abadi which I am not doing. It's not difficult to prove, but it takes long time. So it turns out if you take this definition of measurable sets, then all measurable sets, in fact there are plenty of them, and that forms a sigma G. That is called the Lebesgue sigma G. S bar contains all intervals which are half open. In fact, it contains all intervals, whatever form. S bar therefore contains all open sets, because every open set can be a countable union of intervals in the real line. And S bar is a sigma and zeta. So countable unions are there. So S bar contains the model sigma. So you have two sigma algebras, S, which is the Borel sigma algebra, generated by all open sets. Then you have the Lebesgue sigma algebra, which is all Lebesgue measurement sets, which I have written. And one can show that this is a strict equation. Now on S bar, mu star is a measure. It turns out that mu star is a measure that is countability is okay if we restrict our attention to just S bar. And that is called the Lebesgue measure. So this is how we construct the Lebesgue measure. Of course, I have skipped some 5 hours of lectures probably in these 5 minutes. Every singleton is measurable. This is the intersection of x plus x is 1. I said P is contained in Lebesgue sigma algebra. Countable intersections are always there, therefore singleton X. And what is the measure? Well, subadditivity, and because everything is finite, okay, let's say subadditivity, it's a measure. So this measure is 1 by n, right? So this is the limit of 1 by n as mentioned, because we have a decreasing sequence of sets, all a finite measure, and therefore the measure of the intersection is the limit of the measures, and therefore the measure of every singleton is 0. So every countable set is measurable. Because every countable set is a countable union of singletons. So it is measurable and its measure is 0. Because singletons are all disjoint, so measure of a countable set is the sigma of the measure of each singleton, which is 0, and therefore it is. Every open interval, for instance, I said is measurable. Why is it? Because any AB can be written as intersection so it is measurable. So like that you can one by one do various things. Fine. So now we come to a very, very important property of the Lebesgue measure. So let us take T from R to R. T of x equals alpha x plus beta, where alpha is frequency. It is an affine linear mapping. Yesterday Balu made a lot of noise about linear and no constant term. Okay. So beta alpha x will be a linear map. We add a constant term. We call it first degree polynomial or affine linear map. T is then 1 to 1 only. Because alpha is strictly positive. Beta is any real number. So what is T inverse of x? X by alpha minus alpha x plus beta equals y and solve for x. You get y by alpha minus beta by alpha equals x. So now let us take S to be all Borel sets. This is the sigma algebra containing smallest sigma algebra containing all the open sets. Okay. Now I define T of S is set of all F. So set F equals T a Borel set. So take all Borel sets, take the image under T, that is called T of S. Then T of S is the sigma. X equals T of X, so X belongs to T of S. If I take E is in T of S, sorry, F is in T of S, then F equals T of E. Oh, X is R, sorry. Then what is S complement? This is T of E complement. Because T is a 1-1-on-2 mapping. But if E is a Borel set, E complement is a Borel set because Borel sets is a sigma algebra. So S complement belongs to T of S. Suppose EI Fi is equal to T of Ei, then union Ei is T of union Fi. Is union T of Ei again because T is 1-to-1-on-2. But union is in S and therefore this belongs to Ts. So Ts contains X. It is closed under complementation, it is closed under countable unions. So Ts is a sigma algebra. Maybe this is nothing but T of F, where F is equal to A minus beta by alpha, B minus beta. And if you take that interval A minus beta by alpha, B minus beta by alpha and apply T, then you will get the interval AB. So every open interval is in T of S. T of S is a sigma algebra. So every Borel set is in T of S. So S is contained in T of S. Now T inverse is also a mapping of the same form. Okay? It's also a mapping for 1 by alpha as the constant. So S is also contained with T inverse of S. In other words, Ts is contained in S. So S equals Ts. So what is the conclusion from all this? T is model if and only if T is model. So now you take E is contained in say union EI, I equals 1 to infinity, EI in V. Any set can be covered, we said. Then T of E is contained in union EI equals 1 to infinity, T of EI. Of EI is also in P. Because what is? If you take AB in P, then what is T of E? Conversely, if T of EI is union Fi, I equals 1 to infinity, Fi in V, then E is contained in union T inverse of Fi. And for the same reason, T inverse of Fi is also in V. Because T inverse is a map of the same kind. So whether how do you define mu star of T? This is equal to infimum of sigma mu of Fi, where T is contained in union Fi. That is the definition. But then we have just shown that if Fi is in P, then Fi must be T of EI, where EI is in P. So this is equal to infimum mu of TEI, I equals 1 to infinity, where E is contained in if E is in P, what is T of E? We have it here. And what is mu of T of E? Alpha B minus alpha A. The beta will get cancelled, which is alpha times B minus A, which is alpha times mu of T. So this is infimum sigma alpha times mu of vi where E is contained in union vi. But what is this infimum? How this alpha can come over? It's a constant which is nothing but alpha times. So all this we were doing for any Borel set. Now we take a limit measurements. So let us take any A now. Then mu star of A intersection TE plus mu star of A intersection TE complement. Mu star of A intersection T complement. This is equal to mu star of T inverse A